Check it out now, y'all.
nanoHUB-U, online instruction.
So welcome to week 1 of this course, Thermoelectricity, Atoms to Systems. As you know, this will be taught by 3 of us, myself, Supriyo Datta, then week 2 by Mark Lundstrom, and the last 3 weeks by Ali Shakuri. Now, what I'll be talking about is this bottom-up approach. And in this lecture, let me try to explain a little what that means. Well, thermoelectricity is about current flow due to temperature differences. And in general, when we talk about current flow, usually one starts from macroscopic set of equations. Say something like this. So supposing I have a conductor and you have a voltage applied across it and you want to know what is the current. Usually you'd start from an expression like this. Electric field in the conductor is related to the current density through something called the resistivity, which is again a macroscopic property. And if you look at the inverse of resistivity, that's what you call conductivity. And then people would usually do some kind of microscopic theory, usually based on the Boltzmann equation, which would then give you expressions for the conductivity, which would look something like this. And that function there is the function that would contain information about the microscopic properties. Okay. Now, this approach is what is usually used to describe current flow, and when you talk about thermoelectricity, one extends this equation. So for example, E equals rho J, and then one would add something that would be related to the temperature gradient. And I'm just writing this in one dimension, and that is what you'd call the Seebeck coefficient, and for that also there would be similar expressions. Now, in this course, we are adopting this bottom-up approach, and that's what I'll try to explain, which gives you a lot of insight and a little physical feeling for where expressions like this come from. And that's what I'll be trying to explain. Now, earlier, like about a year ago, we had offered a couple of courses on the fundamentals of nanoelectronics, which was all about this bottom-up approach to nanoelectronics in general. And that course is now available freely, so you are welcome to look at that to brush up on things, or rather to supplement what we'll be doing here. What I'll try to do in this lecture is sort of summarize what went on in like 2 weeks of that previous course. So when you look at the lectures, so next 4 lectures. So what we are talking about here is lecture 1.1. And then there will be 4 more lectures. 1.2, 1.3, 1.4, and 1.5, which were all recorded earlier as part of week 5 of that old course. See? And what I'm trying to do in this lecture is give you a sort of a bird's eye view of the important concepts so that you can follow what comes after this easily. But as I said, if you wanted to go deeper into this material, you should look at the old course. Okay? And that at the end of all this, what I'll do is come back again, and there's be 1.6, where I'll try to summarize it so that you can connect up easily with week 2 when Mark Lundstrom takes over and connects it more to the usual theories of thermoelectricity. Okay. So with that brief introduction, then let me get started. So what is this bottom-up approach? Okay, think of a small device, with 2 contacts across it, and these are the contacts. And at equilibrium, you have a common Fermi energy or this electrochemical potential. And inside this channel, this axis is energy, and what we have plotted here is the density of states. So this tells you what states are available at different energies. At equilibrium, everything is filled up to the electrochemical potential. Everything above it is empty. Now, actually, that's true only at zero temperature. If you are at non-zero temperatures, then the distribution of electrons is given by this Fermi function, which you can draw here. So this is energy axis again. This is the Fermi function, f of E, and it is equal to 1 when you are far above the chemical potential, and equal to 0 when you are far above the chemical potential, and equal to 1 when you are far below the chemical potential. And the transition occurs at the around the chemical potential, but it occurs abruptly if you are at zero temperature. If you are at non-zero temperatures, it occurs over an energy range of the order of a few kT. So that's this Fermi function. And at equilibrium, we have the same Fermi function everywhere. Now, when you apply a voltage across it, that's battery, then the right-hand contact, assuming we have a positive voltage on it, everything here is pulled down. And so we have a different chemical potential. So I'll call this mu1, and this is a different one, which we'll call mu2. And we have a different Fermi function here. So this is F2. And we'll call this F1. And this is energy again, and this is mu2. So this is the diagram when you are out of equilibrium. You've actually applied a potential across this device. Now, why does current flow? The way you think about it for small devices, it's a very clear physical picture actually. It's like this. If you think of the levels here, this contact wants to fill them up. Why? Because their energy is below their electrochemical potential. And so this contact fills them up, sends electrons in, fills them up. This contact, though, likes to keep them empty because the electrochemical potential is below that energy. And so this contact pulls them out. And this just goes on forever. This contact keeps putting in electrons, this contact keeps pulling it out. What is pulled out then flows out into the external contact, and a new one comes in. This just goes on. Now, it looks like a very simple explanation, but this is an explanation that also gives you an understanding of other things that ordinarily cause a lot of confusion. And that is, what about levels down here? Should they be conducting? Well, you see, if you look at any freshman physics text, they will say, why does current flow? Well, because of electric fields. Because when you put a voltage, there's an electric field. Now, if there's an electric field, then ordinarily you might say, well, there's an electric field, so all electrons should feel that electric field and should flow. And that is wrong, because everyone knows that doesn't happen. Filled bands don't conduct. See? But it's not quite easy to understand what happened here. But from this point of view, you see, the point of view I just described to you, it's very clear why there's no current flow here. Why? Because these levels are way below this electrochemical potential, so this contact wants to fill it up, but they are also way below this electrochemical potential. And so this also wants to fill it up. And so they just stay full, that's all. So no current flows, they just stay full forever. So the current flows only around the electrochemical potential up here. And the reason is, this is where the two contacts have sort of two different agendas. One wants to fill up the levels and one wants to empty it. See? Now, this idea we can put on a quantitative footing easily if we assume that electrons go from one contact to another without exchanging any energy with the surroundings. Now, that is a very important assumption. You see, that's ordinarily in big conductors you couldn't do that, because in big conductors, as electrons move along, they dissipate energy, because it's like a ship moving through water. You generate all kinds of waves in the surroundings. So all these atoms take up energy from the electrons and start jiggling. That's what generates heat. And that's what you'd call the I²R loss. And usually people associate with any resistor this heating, the I²R associated. The two kind of come together in people's minds, except that what is now seems quite well established is that in small conductors you can separate them. It is as if electrons go through the channel almost without exchanging any energy, but then it is at the ends where they lose their energy. This is where all the heating occurs. It is what the two ends. And I'd say there is experimental evidence for this, in the sense that what people find is when they apply voltages across small carbon nanotubes, if all the I²R heating were actually occurring in the nanotube, it would have burnt up. And the feeling is the reason it doesn't burn up is because a lot of the heating is actually at the ends, which are large contacts which can get rid of all that heat. The nanotube itself is a small thing and cannot get rid of heat easily. And so if all the heating was inside, it would have burnt up. See? So I'd say for small devices, it seems like at least a good approximation, good first approximation to say that all the heating appears at the end, and the current flow in this region is essentially, what the technical term is, elastic. Elastic means it does not exchange energy. Now, under those conditions, we can write an expression for the current in a relatively simple way. Because what you could then say is, for an elastic resistor, we could say that consider a small energy range dE. And in this energy range, how much current you get depends on the difference between the Fermi functions at the two ends. So it will be F1 minus F2. Just at the two ends. And there will be some constant here, which we'll talk about in a minute. But because electrons do not exchange energy as they go along, I can write the current through this energy range without worrying about the other ones. They're all independent things. They're all in parallel. And so when I want the total current, all I have to do is just integrate this. Because this is what tells me the current in the small range. And if I want the total, just add it up. And this is something I can do only in an elastic resistor, not otherwise. Okay? Now, from here, how do I get an expression for conductance? Well, that's where we need a bit of algebra, which I won't go through here. This is part of one of the homework problems which are discussed in the tutorial lectures. I believe this will be like 1.2. And what is shown in those lectures is that for small voltages, you can approximate F1 minus F2 as negative derivative of F with respect to E. So F1 and F2 are the Fermi functions in the two contacts, and we are assuming that the voltage applied is small enough that you can make this approximation. And as I said, the approximation is described in tutorial 1.2. This is dF dE. And which F do I use? Well, the average between the two, whatever it was in equilibrium. So I'll call that del F0. And times mu1 minus mu2. That's the difference between the two electrochemical potentials, which can be written as Q times the applied voltage. So now you get a current that is proportional to the voltage. So what I can do is, I can divide the current by voltage, and I'll take this off, and I'll just replace this here. So you'll have minus dF0 dE and times Q. So this then gives you an expression for the conductance. Now the point you'll note is that this argument, how it leads you to this derivative of the Fermi function. And the derivative of a Fermi function typically looks like, you see, if you look at this Fermi function, the derivative is 0 down here, 0 up here, and it is only around the chemical potential that it is non-zero. So derivative of the Fermi function looks something like this. And what this function does is it reflects the fact that this is the energy range where all the conduction takes place. Down here really doesn't matter. And this is not a new result. You see, remember I started by showing you the usual expression for conductivity which comes from the Boltzmann equation. And that has this dFdE. So this is a standard result. As I said, the results we'll get are not new. It is just the way of looking at it. It's just that ordinarily when you look at this derivation, it may not be apparent to you why the derivative matters. Why not the actual number of electrons or the Fermi function itself? But when you think of it from the bottom-up point of view, you get it automatically. It's this F1 minus F2, and then F1 minus F2 is approximated this way. Okay. The next question then is, what is this constant in here? This thing, which represents how easily electrons can flow at a given energy. Now this is where you can get a quick answer something like this. That around here, think of the situation at low temperatures. So all the current is flowing between mu1 and mu2, right around here. And the question is, how much, what do you expect this current to be? And the expression could be written something like this. You could say that if I had just one level over here, then the current through that level would have been Q divided by T, where T is the time it takes for an electron to get from here to there. That should be the current through one level. Well, how many levels do I have here? Well, you could say the number of levels you have here is the density of states times this energy range. So it will be something like density of states times the energy range we are talking about, which is mu1 minus mu2, or QD over 2. If we are just talking of an energy dE, we could just write QD over T times dE. Example. Now, there's one subtlety here, and that is, it should be half of the density of states. And the reason we use half is something like this, that all these states, usually there's half of them which carry current in one direction, and the other half carry current in the opposite direction. So kind of like the lanes on a highway. There's a northbound lanes and there's southbound lanes. And when current flows from left to right, so you got lots of electrons trying to get on from here and trying to go there, and no electrons trying to come back, it is the lanes of one going left to right are all filled, but the lanes going right to left are all empty. And so you're kind of using just half the density of states. So that's why you usually have a 2 there, divided by 2. And the time is easy to write down if you are considering ballistic transport. The time is simply L over V. So you could write here L and V. So L is the length of this channel, and V is the velocity of the electron in the channel. Now, of course, inside the channel at a given energy, you have electrons not just going straight at the other contact, but also things that are going at an angle. And so what matters is V cosine theta, and you have to average over the angles. But details like that I'm not getting into. They're kind of discussed a little bit in the tutorial problems. Now here, all I want to point out is that this quantity here should look something like Q dV over 2L for ballistic transport. And I had another Q here, so I'll maybe put it here. Q squared dV over 2L. And this is what you might call the ballistic conductance. Now, so far, this entire discussion has been what you might call semi-classical. It's not fully classical because, of course, I'm assuming some density of states. And usually that density of states contains quantum mechanical input because it might involve effective mass or other knowledge about the energy states. But given the density of states, you're thinking of electrons just semi-classically as particles on a highway. And from that you get this expression Q squared dV over 2L. Now, this is something we do in week 1 of that old course. And in week 2 of that old course, what we show is that if you now adopt a model for the electronic states, and then put in the wave condition meaning that electrons are waves, and so if you have a box of length L, the wavelength must fit into the box. So with every electron with a certain momentum p, you associate a de Broglie wavelength h over p, and say that the wavelength must fit in, then that allows you to actually calculate density of states. And this is the thing that if you are doing it properly from a quantum model, you'd start from Schrodinger equation. On the other hand, if you want to get a quick answer, you could just say, well, we are going to fit the wavelengths into that box. Now, and this is what's done in week 2 of that old course. And what is shown there is that in 1D, this dV over 2L becomes an integer m over h. And this is what's called the number of modes. So this quantity here for ballistic transport, you see, is density of states times velocity. That makes a lot of sense. We are talking of current flow, depends on how many states you have, depends on how fast they move. But that product can be written as this Planck's constant 1 over h times m. And this m is called the number of modes. And if you had a one-dimensional conductor, that m is just 1. But if you had a two-dimensional conductor, something like this, say, then m actually is equal to the number of wavelengths that fit into that width. And if it's a three-dimensional conductor, so this actually is a cross-section, then m depends on how many wavelengths again fit into the cross-section. See? So there are two ways of thinking of m then. One is as density of states times velocity, and the other is as how many wavelengths fit into the cross-section. And these are, and the equivalence of the two, that's not at all obvious. As I said, that is kind of what I did in week 2 of the last course. So if you accept this then you can see that the ballistic conductance can be written as, I could take off the dV over 2L from here and write it as Q squared over h times m. So that would be the ballistic conductance. Now, what about the conductance in a conductor that's not ballistic? Not ballistic meaning where an electron goes through from here to here, not directly, but after scattering many times. That's what you might call a diffusive conductor. Note that I'm still assuming it is elastic. Elastic meaning doesn't change energy. But it could be changing momentum many times. You see, if something is going at 60 miles per hour this way, and then it turns around and goes at 60 miles per hour the other way, the momentum has changed completely. But the energy is still the same. See? So we are assuming that electrons are going elastically because it is only with that assumption that we'd have this simple expression. But you could be losing momentum many times in the process. Now, if that's the case, then what can be shown, and again, this is done in the old course, is that the conductance, as you might expect, would be a little less. But how much less? Well, it would be given by this mean free path divided by L plus the mean free path. So L is the length of the device, And MFP, the mean free path, is how far an electron goes before it gets scattered. So if you had a very short device compared to a mean free path, then you say I can drop this and this is just 1, and you have the ballistic conductance. If you had a very long device, then you can drop this. And then the conductance would actually go down with length, which is of course exactly what you expect from Ohm's law. What you learn from Ohm's law is that the conductance should be sigma A conductivity times the area divided by length. And of course what modern nanoelectronics has taught us is that this isn't quite right, because this would tell you that as L tends to 0, conductance should go to infinity, which it doesn't. It goes to some finite value, and that's because the correct expression is more like L plus the mean free path. But then, if you have a long conductor, Ohm's law holds. So when you accept, from this point of view then, you get a different view of what conductivity stands for. But you'll notice that the expression we now have looks a lot like the standard expressions here that you'd ordinarily have seen coming from the Boltzmann equation. See? But we have obtained it with much less mathematical effort. And the reason we are able to obtain it with much less mathematical effort is because we have assumed an elastic resistor where we have decoupled the mechanical part from the heat dissipation part. And one question you might have is this relevant to big resistors? And the answer is that actually long resistors also you could think of as many short resistors in series. And we can extract the value of conductivity by kind of considering one of these short resistors, which is like what we are doing here. And the answer we get is exactly what you'd have got anyway if you had started from the Boltzmann equation and done it the usual way. As I say, the results are not different. It's just a way of looking at it. So with that little introduction then, I think you can go on to the next 4 lectures, which are taken from my old course on thermoelectricity. And those show you how you obtain expressions for the Seebeck coefficient, and also how you write down the heat current. So if you remember, what we did was we wrote the ordinary current as proportional to something times F1 minus F2, and then we said that if there's a voltage difference, you can write this as dF dE times the voltage. Well, what we'll do in the next few lectures is we'll see what happens to the current when F1 minus F2 is not because of voltage differences, but because of temperature differences. It's the same equation we'll start from, but we'll assume that the difference comes from temperature. And then we'll also talk about what the heat current looks like. And from these, we'll obtain all the expressions for all the coefficients. So that's what we'll be doing in the next 4 lectures taken from the old course. And then I'll come back in 1.6 and try to kind of summarize it and connect it up to what Mark Lundstrom will be talking about in week 2. Thank you.